As high-performance computing systems drive ever larger swaths of science, the slowdown in hardware performance improvements threatens the pace of scientific discovery. As shown here, the annual hardware-driven performance improvements on the spec CPU benchmark plummeted from 52% in the 90s to just 3% by 2015. And as a result of this slowdown in hardware-driven performance improvements, the importance of software solutions to improve application performance has grown. Now, as most scientific simulations are written in compiled languages such as C, C++, and even Fortran, compiler-driven performance improvements can have massive reach. But compilers who have to make decisions ahead of time for all possible values a variable can take are limited in the set of optimizations they can make. But just-in-time compilation, where compilation happens at runtime when all values are known, is a promising approach to deliver performance. Now, to demonstrate the potential, let's take a look at the code here, which just accumulates a value derived from the log of x into r n times in a loop. And the value that we accumulate each iteration depends on a Boolean c. Now, our ahead-of-time compiler, without knowing the values of n, c, and x, can't do much to optimize this loop. But if we're instead compiling at runtime, well, then we can know that c is true, x and n are 10. Then we can fully eliminate the branch and unroll the loop. And in fact, an optimizing compiler will notice that the loop just computes the value 10 with these runtime values and can be eliminated entirely. Now, given this promise, a proliferation of ways to provide code to a JIT compiler have been proposed. But as they're all implemented on different compiler backends and versions, direct comparisons between these systems are unfair, and the strengths and weaknesses of different JIT approaches is unknown. Now, in this paper, we implement the three main classes of JIT front-end: annotating or decorating kernels with the JIT specification, runtime compilation of C++ source code strings, and an embedded DSL that directly constructs code at runtime on the same Proteus JIT compiler, which uses the LLVM compiler infrastructure. And overall, our study reveals that when compilation results are cached and can be reused, the diverse front ends deliver equivalent performance. Across a diverse benchmark suite, we observe up to 7.4 times end-to-end speedup on an AMD platform using MI300 APUs, and up to 1.8x speedup on a platform with NVIDIA H100s. Now, for the more interesting results, including how and when these different front ends perform differently, well, you'll just have to come and see the talk. I hope to see you there.